Newton's laws explain a lot about the world that we see today. From the motion of planets to rocket ships, Newton's equations can accurately describe the world that we observe every day. However, something Newton was not able to do was explain why things move the way that they do. More specifically, he had a very challenging time explaining gravity. Though he could predict the effects of gravity very well, he wasn't able to explain why his equations worked. The whole scientific world had to wait 250 years before Albert Einstein could explain the nature of gravity.
While working at the Swiss Patent Office, Einstein developed his theory of special relativity, which led him to understand the nature of gravity. His work in special relativity concluded that nothing can travel faster than light. This contradicted Newton's theory of gravity.
要理解这一点，想象一个行星系统，想象一下，当太阳蒸发并且完全消失，牛顿的理论预言，当太阳完全消失时，行星将立即飞离它的轨道。牛顿把重力当作一个力，并且这个力可以是瞬间施加在任何一个距离上，这意味着我们将感受到太阳引力消失的影响。
أينشتاين يعرف أنه الضوء ما يتحرك بسرعة كل سريعة. هو يعرف أنه تأخر 8 دقائق من الضوء من الشمس توصل للأرض. ولما أينشتاين يعرف أنه ولا شيء يتحرك أسرع من الضوء، شلون يقدر الأرض تطلع من الحركة مال المدورة دار الشمس قبل ما الضوء مال الشمس توصل للأرض.
Because nothing can travel faster than light, it meant the 250-year-old Newtonian picture of gravity was wrong. The problem was, why do the planets have the orbit that they do? Einstein came up with a new picture of the universe where gravity does not exceed the speed of light. Einstein began to think of the 3 dimensions of space and a single dimension of time together as a single fabric of space-time. We could talk about how things move along surfaces of the space-time fabric. Just like a trampoline, this fabric is warped and stretched by heavy objects like planets and stars. And this warping or curving of space-time is what we feel as gravity. The Earth, for example, is kept in orbit because it follows curves in the spatial fabric, which are caused by the sun.
Now, when the sun disappears, the gravitational disturbance will form a wave that travels across the spatial fabric, much like when a pebble is dropped into a pond and creates ripples that travel across the surface of the water. Therefore, we wouldn't feel a change in our orbit around the sun until the wave reached Earth. Einstein also calculated that these waves traveled exactly at the speed of light. Einstein called this new picture of gravity general relativity.
Central to the general theory is the Mach's principle. Ernest Mach suggested that inertial force and gravitational force are equivalent. There was evidence for this assumption, since Galileo reportedly dropped objects of different masses from the Leaning Tower of Pisa, and concluded that acceleration of free fall is the same for all objects.
质量概念可以以2种不同的形式出现。从惯性的角度出发，所有物体都趋向于保留它们原来的运动，而这种惰性运动可以被测量并称为惯性质量，被牛顿第2定律所量化。质量的概念可以从万有引力的角度来出发，比如说2个有相距一定距离的质量，而且质量也可以被当成物体的一个特性，被称为重力质量。
زي خد أينشتاين ماكو تجربة أي شخص يصنع على مود يعرف إذا الدفع تجي من الجاذبية أو سرعة مع شخص. فكرة أينشتاين ما توازن تقول ماكو تجربة تعرف الفرق بين الجاذبية أو دفع السرعة. نظرة أينشتاين تقول بس حركة بالنظر تقدر تستعمل.
The general theory predicts that light will be bent by gravity. Imagine a person is in an accelerating spaceship far away from any mass. A ray of light enters through a window at the point A in the diagram. Because of the acceleration of the ship, the light will strike the opposite wall at point B, which is below A. To the person in the ship, the path of the light ray will therefore appear to be bent. In the second diagram, a spaceship is at rest on the surface of the Earth. If the Einstein principle of equivalence is correct, then the situation cannot be distinguished from the first situation. The path of a light beam entering a window of the spaceship will therefore also appear to be bent. The prediction is therefore that light that passes close to large masses will have its path altered.
Einstein suggested a method by which the effect of gravity on the path of light could be detected. Einstein suggested measuring the position of a particular star, say in June, and then again 6 months later when the Earth is on the other side of the Sun relative to the star. The path of the light from the star reaching Earth, according to Einstein, should now be bent as it passes close to the Sun. This will cause an apparent shift in the position of the star. Einstein predicted that the path of starlight should be deflected by 1.75 seconds of arc as it passes by the Sun. To observe starlight that passes close to the Sun, then the stars must be observed during the day, and the only way that this can be done is during a total eclipse of the Sun.
The general theory was published in 1917, and by good fortune, a total eclipse of the Sun was predicted for 29 March 1919, near the Gulf of Guinea in northern Brazil. Expeditions were mounted to both destinations, and scientists were able to collect enough photographs of suitable stars to test Einstein's prediction. The location of the stars indicated that the path of the lights had indeed been deviated by 1.64 seconds of arc, a result that compared very favorably with Einstein's prediction.
广域相对论可以预测到黑洞的存在，在它们的寿命中，它们会经历一个崩溃阶段。在它们崩溃时，它们的密度上升，而且因此它们的表面积增大。 而且辐射离开了它们的表面，在其周围时间空间变得越来越曲折时，辐射的路径变得越来越弯曲。如果表面的重力上升到足够的程度时，射线的路径会变得非常曲折，而且没有射线可以脱离其表面，而且这个星体就会完全变成了一个黑洞。
من غير نظرة نقدر نباوع على حفرة سوداء من سرعة الإطلاق. نجمة تتحول إلى حفرة سوداء لما سرعة الإطلاق توصل إلى سرعة الضوء. الراديوس لما نجمة تتحول إلى حفرة سوداء معروف كسوارتزشايلد راديوس، وبصنفه ميكانيك مال نيوتن تنطي نفس الرقم.
If no radiation can leave a black hole, and all radiation falling on it will also be trapped, how can such things be detected if they exist? One possibility is to observe a black hole as a companion to a binary star system, a star system consisting of two stars orbiting their common center of mass. Another way is to observe the effect that a black hole has on high-frequency gamma radiation as it passes close to a black hole. It can be said that at this point in time, astronomers do not doubt the existence of black holes.
If a person is outside the gravitational field of a black hole and observes an event that takes place at distance r from a black hole, then the time for the event will be dilated according to the following equation, where rs is the Schwarzschild radius of the black hole. This effectively means that if a person were to observe a clock approaching a black hole, the motion of the hands of the clock would appear to get slower and slower the closer the clock gets to the event horizon of the black hole. At the event horizon, they would stop moving, and time would stand still. The general theory of relativity is now accepted as being the correct interpretation of gravity and as such the correct model of our view of space and time. General relativity and quantum theory form the two great theories upon which the whole of physics rests. To date, all attempts to unify them into one complete theory have been unsuccessful. And to this we come to a conclusion on our series on Einstein's theory of general relativity.